Here we are going to discuss about the inverse Laplace transform of functions where the denominator has real roots but they are repeating. So in this case also, if you take this example here, so this denominator ds is equal to s plus 3 to the power 4. So if you put ds is equal to 0, so you will have s plus 3 to the power 4 will equal to 0. So you will get s is equal to minus 3, minus 3, minus 3 and minus 3. Since the power of this s plus 3 is 4, then we are indicating that it is a 4 order equation, so it has 4 solution. So all solution will be minus 3. So that means this real roots s is equal to minus 3 is a real root, but this root is repeating. So when this type of function is there, then we have to use the formula of Laplace transform given by this Laplace transform of t to the power n e to the power minus a t ut is equal to factorial n by s plus a to the power n plus 1. So this formula is little bit complicated, but you can keep the track from like this, so that if ut's Laplace transform is 1 by s, the unit step signal Laplace transform is 1 by s, then if you shift this signal e to the power minus a t ut, then you will get 1 by s plus a. Alright, then if you multiply it by t to the power n, this function is multiplied by t to the power n, then your output will be, so you are already getting s plus a, so this will be, if t to the power n is multiplied, then your power of this will be s plus a to the power n plus 1, and in the numerator you have to write factorial of n. So factorial of n, this you have known, factorial of n. Suppose factorial of 2, you have to write like this: 2 into 1. Factorial of 3 is equal to 3 into 2 into 1. So this factorial calculation you already know. So in this factorial n you have to put here. So now suppose for the first function x is equal to 1 by s plus 3 to the power 4, if you want to make this function x is equal to s plus 3 to the power 4 in the order of this, then you can assume that this a is equal to 3, and here if you want to make this n plus 1, it can be written as t plus 1, so n will be equal to 3, so a and n equal to 3. So when this denominator is okay, s plus 3 to the power t plus 1, you will be directly obtaining from this. But to make this factorial n in this function, so n is equal to 3, so factorial n you have to write here factorial 3. So since you are multiplying factorial 3 here, so you have to divide it in the outside, so that they be cancelled out and you will ultimately get this one. So we're converting this function to this to make it compatible with this one. Okay, so now you can see that this factorial 3 by s plus 3 by to the power 3 plus 1 s plus 3 to the power t plus 1. So this is n, this is n, and this is a. So if you take the inverse Laplace transform of this, you will get t to the power n means to the power 3, and e to the power minus a t means e to the power minus 3t ut. Okay, so that is what we are doing. Xt is inverse transform of xs, so xs is this one, so 1 by 3 factorial is a constant, so we have taken this outside and we are taking the inverse Laplace transform of this part. So this part's inverse Laplace transform is nothing but t cube, t to the power n means t cube, e to the power minus a t means e to the power minus 3t ut, and this factorial 1 by factorial 3 means 1 by 6. So you can write xt is equal to 1 by 6 t cube e to the power minus 3t ut. So there will be bracket here. So this is the ultimate solution of this function given here. So you can also do this second example by same approach. So just you have to make this function compatible into this format so that you can get a value and a n value and factorial n value in the numerator, and whatever the values you want to put here, and then same value you can divide in the outside, so that will be a constant, so that is not a issue. Okay, so you can get a formatted like this, and you can use the property of inverse Laplace transform of this as this to get the inverse Laplace transform of the given function. So this is a technique where there is a repeated roots, real roots present. Okay, we can use this technique to find the inverse Laplace transform.